Okay, hi everyone. I'm Paul Chignon, and today I'm going to talk about a new option of strace, seccomp BPF. So if you've been staying in this room for the last two talks, you've already heard about seccomp BPF, but in this talk, I'm going to go into the details of how it works behind the hood, under the hood. So as an overview of this talk, I'm going to first go into explaining how strace uses ptrace to stop at syscalls. Then I'm going to explain how it uses seccomp BPF to stop only at syscalls of interest. So that's what the option is doing. And finally, we're going to see, while we're talking about this, we're going to see the two cBPF algorithms that are being used to decide on which syscalls to stop. So strace default behavior. So at the top of the slide, you've got the thread that you're trying to trace, the tracey and strace. So when you start tracing this tracey process, first it's going to do some initialization with regard with ptrace. And then when it's ready to start the tracey, it's going to start it with a ptrace command known as ptrace syscall. So what this command is going to do is stop the tracey at each syscall entry and exit. So for instance, if my tracey starts, it's going to do some processing in user space, for instance. And then when it gets into the kernel mode with a syscall, it's going to, ptrace is going to stop the tracey, stop it with a syscall entry stop event, and then give control to strace in user space. So then once strace is done processing this syscall entry, it's going to restart it again with ptrace syscall to stop at the syscall exit this time. So it's going to keep doing this. So every time you stop, you have two context switches, to and from strace in user space, and then of course two stops per syscall. So what's the issue here? So the issue comes to light if you think about the trace qualifier. So the trace qualifier is a way to select which syscalls you'd like to see. So for instance, if you only want to see the seccomp syscall, you're going to do -e trace equals seccomp. You can do the same with -e seccomp. And then you've got some other aliases, for instance, for all of the network-related syscalls, such as percentage network. However, when you're doing this, it's still going to stop twice per syscall at all syscalls. So even if you don't want to see the read syscall, for instance, it's still going to stop at all of the read syscalls. So as I said, this involves two context switches. It's very, very expensive. So we've seen in previous talks some examples with DD, so that's probably one of the worst cases. But if you're trying to do, for instance, compile a Linux kernel, so on my old computer it took about 12 minutes. If I'm trying to do the same with strace, even if I'm trying to see only a single syscall, so the connect one in this case, it's going to take 24 minutes, so double that. So we need a way to tell the kernel at which syscalls we want to stop. And we need to do this in the kernel because obviously it's the kernel that is going to decide when to stop. If we do this in user space, it's too late. We'll already stop. So we need a way to do this in the kernel. So from the name of the option, you've probably guessed that we're going to use seccomp BPF. So seccomp is a way to filter syscalls in the kernel. It's meant for sandboxing. One of the first users, in particular, of seccomp BPF is the Chrome sandbox. So seccomp BPF allows you to choose which syscalls you want to filter, so which syscalls you want to allow and what you want to do otherwise. As a side note, seccomp BPF is the second user of BPF in the Linux kernel after the socket filters, but before all of the other eBPF stuff you've probably heard about. And it's cBPF in seccomp BPF. It's not eBPF, so it's very much limited compared to what eBPF can do. Okay, so one example, if you want to allow a process to do open and open at syscalls, but you want to kill it if it tries anything else, you're going to load this small BPF program, cBPF program in the kernel. So the third line is actually loading the syscall number. So it's the NR field of seccomp data. Then you're going to compare that with 257, which is open at, and then 2, which is open. And that's only true on the x86-64 architecture. Once you've done that, you're going to jump either to bad or good. So bad would be we're killing this thread, and good is simply we're allowing this syscall, so we're just going to do the usual processing of the syscall in the kernel. Now, if you want to do pretty much the same thing, but this time you want to allow specific accesses, you want to allow processes to open specific files, you're going to need help from user space because you need to go and look into the file path, for instance, to take your decision. So in order to do this, you're going to change slightly the program. This time, instead of returning ret allow to continue processing the syscall, you're going to return ret trace. And in this case, seccomp is going to call into ptrace to stop your tracee, your process, and it's going to give control to a ptracer in user space. So in our case, it might be strace. Okay, so strace, seccomp bpf. So the behavior changes a little. So if we take the same scheme as before, we're going to start in user space. Strace is doing some initialization. And when it's done, it's going to start the tracee, this time with the ptrace count command. So what this is telling is simply that the tracee is supposed to behave as usual. It's not going to stop at any syscalls. It should just process the syscalls and do whatever it does. So the tracee can do syscalls, can do some processing in the space. It can do syscalls. If we're not interested in the syscalls, we're still going to have the BPF program that is going to run to determine if the syscall is of interest or not. If it's not of interest, it's simply going to allow the syscall and let it go. So we can do some processing like this. But once we get in the kernel with a syscall of interest, the cBPF program is going to return ret trace. And in this case, we're going to have a second stop. So it's a different event from the previous stops we had. And this is going to give control to strace in user space with a context switch. Once strace is done doing the processing for this syscall entry, it's going to restart the process with ptrace syscall. And the reason we can't use ptrace continue for this, to go to the exit of the syscall is simply because seccomp bpf does not run on syscall exits. So seccomp bpf is meant for sandboxing, so you usually want to limit which syscall entries you can do and not which syscall exits you can do. Okay, so it's going to keep doing this. Once we exit the syscall, it's going to restart it with ptrace continue again because we know that we can stop with the seccomp bpf program at the next entry to a syscall. There's one caveat to this, however. In Linux, before Linux 4.8, the second stop happened before the syscall entry. So what that means is that we can do the same as before, so we can restart it with ptrace continue at first. But then once we reach the second stop, we have to restart it with ptrace syscall to get to the entry, and then again to get to the exit. And because of that, in Linux before 4.8, we have 2 stops per syscall instead of 1 when the seccomp bpf option is enabled. Okay, so what about the cBPF programs? Because I talked about how we changed the way we stop the process, but I haven't talked about the cBPF program itself. So one first naive way to do it would be to do a linear search through all of the different syscall numbers we're interested in. So for instance, here, if I'm interested in read, write, open, close stat, and fstat, I'm going to go over all of the different numbers, and if the syscall number, so the NR field of seccomp data matches one of these, I'm going to jump to trace and return the return code that we need. So is this optimal? Obviously not. So this is O of n. If we want to improve it a little, there's one obvious optimization here. We can simply optimize a contiguous set of syscalls. So for instance, I was going from 0 to 5. I could simply check that my syscall number is between 0 and 5. And if that's the case, I can just jump to the trace command. So what we're trying to optimize here is the size of the program, because in cBPF, instead of eBPF, we're limited in how many instructions we can have in our BPF program. So we're limited to, I think, 4K instructions. And therefore, we have to ensure that our programs are as small as possible, because they're first going to be faster to execute in most cases, but mostly because we want to ensure that we can load the BPF program in the kernel. Okay, is that the best we can do? In some cases, it's still not the best we can do. So what is the worst case of this? If we have some user that is trying to trace all odd-numbered syscalls, we are not going to be able to use this optimization, and we're going to have a lot of different instructions to compare the syscall numbers. So what we can do instead is, since in CBPF we have 32-bit bitwise operations, we can encode the syscall numbers that we're interested in into 32-bit bit arrays. And then we're going to go over all of these bit arrays and compare our syscall number with the appropriate offset in the bit array. So basically here, if I want to trace select on IOCTL, I'm going to set the bit corresponding in the given bit array. So this is the first bit array in this case, because they're select on IOCTL of small number. And then we're going to go over all of the different bit arrays with our BPF program, and we're going to select the appropriate offset once we reach the appropriate bit array, and we're going to check if it's to 1 or 0. So the reason we can't jump directly to the bit array that we're interested in is that in CBPF you do not have indirect jumps. So you have to implement your switch case as an if-else and going over all of the different cases. Okay, so we compared the two different algorithms with different set of syscalls filtered. So the first one is just none, and ptrace, and not ptrace, basically everything except ptrace. And then we've got some cases with aliases that I mentioned earlier. The last one is just a combination of different aliases to get a larger number of syscalls. So what we can see is that in most cases, the linear algorithm with the optimization I mentioned generates much smaller programs than the binary match. In some cases, however, when we have a large number of syscalls in particular, the binary match is going to give a better result. So the reason for this is that in the case of the binary match, we have to do some pre-processing on the syscall number to get the appropriate offset, and then the bit array, we have to encode all the bit arrays. So this is more or less constant-size programs, but there is still a lot of processing to do, even if you have only a single syscall filter. So what we did in strace is we generate both programs when we start strace, and then we're going to decide based on which is the smallest. We're going to load the smallest in the kernel in order to get the best of both approaches. Okay, some limitations of this option. So the first limitation, which Dimitri already mentioned, is that seccomp BPF implies -f. So -f, strace -f, means that you're going to trace all of the children of your trace process when they fork, when they clone. So the reason for that is that in the kernel, the children inherit a seccomp filter chain of program from their parents. And the way they do this in the kernel is that they give simply a reference to the beginning of the chain to the children. So each children in the kernel will have a reference to the seccomp filter chain of the parents. And however, if we have a chain, for instance, of seccomp filters 1, 2, 3, 4, but we only want to inherit 1, 2, and 4 because the third one is the strace program, the strace BPF program. So we don't want to inherit it for children. If we want to do this, we'll have to reconstruct the chain to have 1, 2, and 4. So we want to skip the third one. And we can't do this with references in the kernel. So currently, there's no good way to do this, except if we make copies. But then there's a lot of overhead to copying the whole chain of seccomp filters. Okay, the second limitation of this option is -p. So if you want to trace an existing process, you cannot use today the seccomp BPF option. The reason for that is very simple. There's currently no way to attach a seccomp BPF program to an already running process in the Linux kernel. There is, however, a way to, when you attach a program to a thread of a group of threads, there is a way to synchronize the seccomp BPF programs across all threads in the group. So maybe there is some hackish way to do this, but yeah, not sure. Okay, to conclude, to sum up first, we've seen that strace stops at all syscalls by default, and that's very, very expensive because of context switches. In addition, we've seen that the seccomp BPF option, when you're using filters on your syscalls, allows you to stop only at syscalls of interest. And we've seen the two different seccomp BPF algorithms that we're using in strace to do this, to implement this match over syscalls. There are, however, some things that could be improved in the current implementation that are pretty straightforward. So the first one is on some architectures, you've got system calls like socket call and IPC, which allow you to do basically other syscalls. So you would have the first argument of socket call, for instance, would tell you which syscall to actually do. So for instance, do a connect or maybe something like this. Currently, this is not supported in the CBPF program because you would have to match on the first argument of the syscalls. You would have to match on the number that is the first argument of socket call, for instance. The second thing that could be done is the strace-c option, which currently allows you to print a summary of statistics on your syscalls. This is a perfect use case for eBPF instead of CBPF. Because eBPF allows you to aggregate data in the kernel, and therefore it could allow you to aggregate statistics for this option to only send them to the strace process at the end. So instead of sending everything to the strace process and stopping all the time, you could only send a summary of these statistics. Okay, so I've been a bit fast, so we have plenty of time for questions. I hope you have some, and thanks for listening. Sorry?
Did you run the kernel compilation benchmark with seccomp BPF?
Yeah, I did. So I don't have the numbers. So the question is, did I run the seccomp BPF benchmark with the... Did I run, sorry, the Linux compilation benchmark with the seccomp BPF option? I did. I don't have the numbers here, but might have them online. Okay. So here, if you can see, the one before last, so the second one is the number with seccomp BPF. So it has a few seconds, but yeah, nothing much.
Yeah. You talked about eBPF and CBPF. Is that a limitation of what seccomp allows currently supports in the kernel?
Yeah, so the question is, I've talked about CBPF and eBPF and whether that is a limitation of what seccomp allows in the kernel. So seccomp only allows CBPF programs in the kernel. There's been some discussion to allow eBPF on the mailing list, but that's pretty much, I don't think it's going to get there. So the answer was very clearly that this is not something they'd want. The main reason for this, I think, is the unprivileged eBPF programs that this would require, and they don't want any more unprivileged eBPF programs. So. Yeah.
Actually, I have a question. Probably should the service change in the kernel to allow detaching BPF programs from thwarted processes?
So the question is, should we try to upstream some work in the kernel to allow us to detach seccomp BPF programs from processes? I guess we can always try. I don't know if there's any.
I'm afraid it will take about 9 months, as usual.
I think detaching BPF from process will be threat as security issue.
Yeah, that's probably the main concern they're going to raise is the security aspect. So what if? But I don't see how that could be misused, because if you're actually trying to detach a program from your process, I mean, you're asking for it. So maybe you need privileges in order to do that. But
then that could be like a special case when you're tracing, right?
Personally, I don't think this is a security issue, because when you're attaching a program, you can explicitly say that this program should not be inherited. And this way, it wouldn't be any security issue. It will require revoking the kernel. That's why I'm asking this question.
yeah, but then we're going.
We should try this. This would allow to support seccomp BPF with full forks and without, not just with full fork, but also without full forks.
There might be some issues with performance there, because of the way it's implemented in the kernel, it's reference count with. So if we want to remove one from the chain, it's going to be kind of difficult. Yeah. Any other questions? So the next talk is about eBPF this time. So if you want to listen to some eBPF, you have to stay here. Okay. Thanks.